Okay, welcome back, everyone. So today we're going to solve ordinary differential equations using Laplace transforms. On Friday, we're going to start looking into control systems, which are awesome. And then on Monday, we're going to do a little bit more on partial differential equations. Okay, so the fourth homework is due on Friday. The fifth homework will be due next Friday. And the fifth homework will cover Laplace transforms, ordinary differential equations, and it'll probably cover a little bit of Monday's lecture. Okay, because I want you to have some practice before the final, because I'm definitely going to ask you about Laplace transforms and PDEs on the final. Okay. Any questions about what we were doing with Laplace transforms last time? Anything at all? Yeah.
Does the signal have to be stationary?
So we are typically integrating a signal from a fixed initial time to infinity to do the transform, and so we assume that this signal is kind of developed at the point we take the transform. So why don't we do some examples and get a feeling for what you can and can't transform? Maybe you can give me an example. Like, what would you be thinking of that would not be?
EMG, for example. Electrical signals as a time series. Typically, to ensure stationarity through spectral coefficients or spectral transformations of the signal, we would do something called a maximal voluntary contraction, which is an isometric contraction that transforms the signal into a stationary form. And then we can do an FFT. So I was wondering if the same principles apply to Laplace transform.
That's a good question. Yeah, so we're generally assuming that we have a signal that starts at some time, so it's kind of boring beforehand, then it evolves, does something to infinity. There are times we can break this assumption and make kind of a generalization for window data or time series data, but that's a little more complicated. Okay, so last time we derived what I think is the most important property of the Laplace transform, and this is basically directly inherited from the same property of the Fourier transform, which is if I transform the derivative, I just get my Laplace variable times the Laplace transform of the function. So if I have Laplace transform of f prime of, let's make this of time, t, then this is going to equal my Laplace variable s times my Laplace transformed function f bar. But now, because we're integrating from 0 to infinity, I also have this initial condition minus my initial condition f at time 0. Okay, we just derived this last time from the integration by parts. So if I want to do the Laplace transform of f double prime, how do I do that? What's the first step? I mean, this is, you can just say that this is d dt of some function g of t, where g of t is d dt of f of t, right? So I can just do this in two stages. I can say, okay, well, this is going to be s times the Laplace transform of f prime minus f prime at time 0. And what is the Laplace transform of f prime? Well, it's all of this stuff, so I just plug this in, and I get that's s squared times the Laplace transform of f minus s times, this is minus f0, yep, minus s times f0 minus this term here. So I'm just doing like a nested, it's kind of almost like a chain rule. I'm just doing nested Laplace transforms of derivatives, and I get this expression here. That make sense? Yep, we just plugged in Laplace transform of f prime in here. And in general, if I have the Laplace transform of the nth derivative with respect to time, then I'm going to get a big polynomial in S. I'm going to get s to the power n times f bar times the Laplace transform of f minus s to the power n minus 1 times f0 minus s to the power n minus 2 times the first derivative f prime of 0 minus dot 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 minus s times the n minus second derivative of f evaluated at 0 minus the n minus 1th derivative of f evaluated at 0. So superscript here just means I'm taking the derivative that many times. This isn't too hard to show that if you just keep going down the line, this is the form you get. Okay? The upshot is all of these are just numbers. These are these are values of my function and my derivatives. It's kind of like a Taylor series expansion, right? I got a bunch of derivatives and a bunch of evaluations at 0. So I have a big polynomial in S, and this is the only term that has something interesting, my Laplace transform of f. Okay, good. And last time I was a little bit careless, and I think I wrote that these were evaluated at 0 plus, and that's not right. These are evaluated at 0 minus, which means these are evaluated at just to the left point of t equals 0. So if I had something like a step response at time 0, then my value of f at 0 minus is equal to 0. And my value of f at 0 plus is equal to 1, because this thing essentially jumps. Epsilon to the right of 0, it's 1. Epsilon to the left of 0, it's 0. And we want to be using this value, this f of 0 minus value, for all of these derivatives that we're evaluating. Okay. There's some reasons for this. They're good reasons. They're kind of philosophical reasons. You want this to be causal, and so you can't know what's going to happen epsilon from now. You can only know what happened epsilon away behind in time. Okay, so these derivative formulas are extremely useful for solving ODEs. Extremely useful. So I'm going to ask this every time because I can't remember anything. How many of you have used Laplace transforms to solve ODEs before? Okay, how many have not? Okay, good. So you probably haven't seen the kind of general way that I'm going to go about doing this for control systems, so this will probably be new for a lot of you. Okay, so what we're going to do is we're going to revisit a relatively simple example that we've looked at before, which is the spring mass damper system. And just to refresh your memory, we have some fixed wall, and we have a spring, damper, and some mass m. And we're interested in the position of this mass as it's moving back and forth based on Newton's second law. So we can say that the equations of motion are m x double dot plus c x dot plus k x equals 0. And if I introduce some new coordinates, if I introduce the natural frequency and the damping ratio, this is just review. We've totally done this before. Okay, if I introduce these two new variables, then I get a really nice form of the equation. X double dot plus omega naught c x dot plus omega naught squared x equals 0. So why do I like writing this in terms of omega naught and c? They're physical parameters. What do they mean physically?
Natural frequency and damping ratio.
Right, so natural frequency omega and damping ratio zeta, so what this means is that I can vary these independently. And if I just vary omega naught, then that changes the frequency of oscillation. And if I independently vary zeta, then that makes it damp more or less quickly. It's more or less damped with zeta. So these kind of separate the two effects. And if you like to think about this in terms of the eigenvalues of the characteristic equation, zeta would be the real part of the eigenvalue, and omega naught would be the imaginary part. This is how fast the sines and the cosines move, and this is how much exponential decay I have. Okay, so just a review. We've done this example before in 564. But now I'm going to show you that you can solve this really, really easily using Laplace transforms. Okay? So I'm going to essentially pick some numbers to make this system just have numbers in it. So we're going to use x double dot plus 5 x dot plus 4x equals 0. And what other information do I need to make this a well-posed ordinary differential equation? Initial conditions. How many do I need?
Why do I need these?
Second derivative.
So it's a second derivative. I'm going to have two different e to the lambda t's, and they're each going to have a coefficient. And I need two initial conditions to determine my two initial conditions, my two unknown coefficients. Yeah. So let's just pick really easy ones that make all the math work out nicely. Okay. Good. So this is the differential equation. We just picked some omega naught and some zeta. I think omega naught is 2, and zeta is 5/2. Okay. So now we're going to solve this using Laplace transforms. The first step is I'm going to Laplace transform each of these terms, x double dot, x dot, and x. Okay, so just everyone help me. What is the Laplace transform of x dot, double dot? S squared times x bar of s minus s times x naught minus x dot naught. This is just the Laplace transform of x double dot, so I'm going to put brackets around it. Okay, plus 5 times the Laplace transform of x dot. S x bar s minus x naught. Okay. Plus 4 times the Laplace transform of x, which is just x bar. All of that equals 0. So I want to color code this just because it's a little easier to understand when we color code. This is the Laplace transform of x double dot. This is the Laplace transform of x dot. And this is the Laplace transform of x of t. So all I've done is just Laplace transform both sides. If I multiply by a constant, remember my Laplace transform is linear. So if I Laplace transform this term plus a number times this term plus a number times this term, it's the same as Laplace transforming this plus 5 times the Laplace transform of this plus 4 times the Laplace transform of this, because it's linear. Okay? Just like the Fourier transform, because it is a Fourier transform, essentially. It's a generalized Fourier transform. Okay, great. So now what would be the sensible thing? What are we trying to solve for in this equation? X bar. Right? X bar is essentially my solution, but in the frequency domain. So I want to solve for x bar, and then I'm going to inverse Laplace transform it. So let's just collect all of my s bar stuff on this side. So I have s squared plus 5s plus 4. I have all of that times x bar. And then I have everything else. Everything else that doesn't have an x bar, I'm going to put on the right-hand side. So I'm going to say that this equals, and all of these terms that don't have an x bar, I'm just going to move over to the right-hand side. And I'm also going to plug in numbers at this point, because x naught and x naught dot are numbers. Okay, so I have so minus 2s. I'm going to bring that over, and I get a plus 2s. And then I have a minus 5 is plus 5. And a plus 5 times a minus 2. Okay, so plus 5 and minus 10 is minus 5. I'm going to bring that over and get a plus 5. Should I do that again? Was that super confusing? I'm evaluating this. This is minus 5 is a plus 5. And 5 times minus 2 is minus 10. So plus 5 minus 10 is minus 5. I add it to both sides. I get 2s plus 5. The reason I'm belaboring this is because I totally messed this up in my notes this morning and got really, really confused. OK, so now this is kind of amazing. We have a few really interesting things happening here. So first of all, what is this expression on the left hand here? This is the characteristic polynomial of this differential equation, right? Remember, if I plugged in x of t equals e to the lambda t, if I just made this assumption and I plugged it into all of these terms, then I would get a characteristic polynomial lambda squared plus 5 lambda plus 4 equals 0. And the solutions of this characteristic polynomial would be my eigenvalues. Okay? And so this is my characteristic polynomial, which is great. And the characteristic polynomial is responsible for telling me everything about the dynamics of this ODE. It tells me what all the timescales are, what all the lambdas are. So all of the dynamics are over here on this side. And all of my initial conditions are on this side. So all of the information about my initial conditions is on this right-hand side. Right? Because every term that was left over that didn't have one of these x bars was in terms of my initial conditions, and I just brought them all over to the right-hand side. So now I have a polynomial in my initial conditions, in terms of my initial conditions, and I have a characteristic polynomial on the left-hand side. So this is starting to look kind of interesting. OK, so what's the last step I need to do? Sorry, say again. So we'll have to inverse Laplace at some point, but that's another step down the road. What's before that?
Get rid of the characteristic equation.
Yeah, so I want to isolate x bar, so I divide by the characteristic polynomial. So I'm going to say, OK, x bar is now equal to 2s plus 5 divided by s squared plus 5s plus 4. And now what I want to do is I want to inverse Laplace transform this thing, right? This is my solution. This is the solution to my ordinary differential equation with those initial conditions, but it's in the frequency domain. So I have to inverse Laplace transform to get this back to a function x of t. But how do I inverse Laplace transform? We did it once. It was kind of horrible. And we only did it for a very simple expression. So we know that the inverse Laplace transform of 1 over s plus a is equal to e to the minus at. This is all we know. This is the only inverse Laplace transform we know, because we actually derived this one when we were doing complex analysis. So what I'm going to try to do is split this polynomial up, this rational expression, up into a sum of first-order monomial fractions. This is called partial fractions. This is how everyone solves ODEs using Laplace transforms. So what we're going to do is we're going to say, well, this is really equal to some stuff over s plus 4 times s plus 1. Now, this is starting to look a lot like how we solve ODEs, right? We're taking our characteristic polynomial. We're factoring it into monomials. Each of these are my eigenvalues. Minus 4 and minus 1 are my lambdas. And what we're going to say is I want to write this as some constant a divided by s plus 4 plus some other constant b divided by s plus 1. And I want to find what is a and what is b. Because I know how to inverse Laplace transform each of these. OK, so how do I do that? We say, OK, so if I have two fractions and I want to add them together, I take a times this denominator plus b times this denominator divided by both denominators. So this is a s plus 1 plus b s plus 4 divided by s plus 1 times s plus 4. And so what we have is that this numerator has to equal this numerator. And so I'm going to solve for the a and the b that make these equal. Okay, so let's just do this. So we have a times s plus 1 plus b times s plus 4 equals 2s plus 5. And I'm going to collect all of the terms with s's and make that an equation. And I'll take all the terms with 1s and I'll make that an equation. So I have a plus b equals 2. as plus bs equals 2s. And I have a plus 4b equals 5. And now I can solve for a and b pretty easily. So how would you do this? What would be the easiest way to solve for this? Yeah, I'm going to subtract one of these from the other one. Let's subtract 1 from 2, so I get 3b equals 3. That's convenient. B equals 1. And if a plus b equals 2 and b is 1, then a is also equal to 1. And so this thing equals 1 over s plus 4 plus 1 over s plus 1. Okay, the final step is now we have x bar of s equals 1 over s plus 1 plus 1 over s plus 4. And I'm going to inverse Laplace transform this. And the great thing about Laplace transforms is that they are linear. So the Laplace transform of this is equal to the Laplace transform of the first term plus the Laplace transform of the second term. So we have x of t, x of time, this is what we want. We want a real solution in time, is equal to the inverse Laplace transform of x bar of s. And that's equal to the inverse Laplace transform of this plus the inverse Laplace transform of this. And we know what each of these are. We know that this first one is e to the minus t, and the second one is e to the minus 4t. Okay, so that's the solution of our ODE. Now, you might be thinking to yourself, this doesn't seem a lot simpler than solving this using the characteristic equation and e to the lambda t. And that's certainly true. This is a lot of steps involved in solving this. But there are a number of reasons why this is a really, really good way to solve ODEs. And I'll tell you a number of these reasons. So first of all, are there any questions about the general procedure? Yeah.
If we run into a case where there's a more complex inverse Laplace transform, will that be, is that given, or do we have to go find it?
Okay. Anytime I have a linear system of ordinary differential equations, I will always have my characteristic polynomial on the denominator. I'll always be able to factor it into s plus lambda 1, s plus lambda 2, s plus lambda 3. I'll always be able to factor it into these monomials and inverse Laplace transform each of them. Almost always. If you get into a nastier situation, like you have a nonlinear differential equation and you're trying to inverse Laplace transform, you would try a lookup table or Mathematica. Okay, so other questions about the Laplace transform? Yeah?
If we had a forcing function here on the right-hand side, would we just Laplace transform that and follow it through?
Good. So this is why we want to be doing things in the Laplace transform domain, because I could add a forcing function u of t, and I would just Laplace transform it, and I would just have a u bar, and this would be my numerator plus u bar, and everything would look the same, except now I'd have a u bar divided by characteristic polynomial. So that's what we're going to do in the end of class and on Friday. So that is one of the key reasons why we want to be working in the frequency domain, because even though it's harder to solve an initial condition problem, it's much, much easier conceptually to add forcing, to add control. So that's something we'll visit in a little bit. It's also really nice because working with this function in the frequency domain gives us a tremendous amount of insights about what the physical system is doing. So on Friday, I'm going to spend most of the time telling you how to gain insight from looking at the solution in the Laplace transform domain. So for example, S can be any complex number, right? S can be I omega or 5 plus I omega or whatever. This can be any complex number you want for S. And so this is a complex valued function with a real part and an imaginary part. And those real parts and imaginary parts have extremely relevant physical intuition for almost all physical systems, for materials, for fluids, for elastics and vibrations. And we're going to get into why we care about this function on Friday. Okay, so even though solving the ODE and getting the time domain solution might be a little hairier, it's still good to go through this intermediate step because it simplifies how we understand the problem. Okay, should I do another simple example? Would that be helpful? Yes? Okay, let's just do a quick one. This one's from Boyce and DePrima. It's even easier, and we can go pretty quickly. Okay. Okay, so the Boyce-DePrima example is also a second order differential equation. It's just x double dot minus x dot plus minus 2x equals 0 with initial conditions x of 0 equals 1 and x dot of 0 equals 0. So we can solve this one super easily. Let's just go through it. What are all of my solutions? What do I do first? Okay, plug in the Laplace transform to each of these. So I get s squared x bar minus s x naught minus x dot naught minus s x bar minus x naught. If I mess up, please tell me. Minus 2x bar equals 0. Okay, next step. Collect all of my x bar terms, my solutions on one side. So I have s squared plus s squared minus s minus 2 times x bar. And all of my initial conditions I'm going to bring over to the right-hand side. So that equals plus 1s, s. X dot is 0. This initial condition is 0, so I'm just going to forget about it. And then minus 1, when I subtract it over, gives me a minus 1. Okay, so I've collected all of my dynamics terms over here, my characteristic polynomial. And these are all of the terms that fell out from my initial conditions. Okay, next step. Divide. X bar of s equals, it's a function of s, it's s minus 1 over s squared minus s minus 1. Minus 2, good. And what does this factor into? So what do I know right off the bat from that the solution is going to be? Going to be unstable. So this is going to be a stable eigenvalue. This is an unstable eigenvalue. So right off the bat, I know that anytime this thing has a denominator 0 that's in the right half plane, positive 2, this is bad news. Okay, good. And finally, I'm going to write this as a over s minus 2 plus b over s plus 1. Okay? So let's solve for a and b. Well, we have a times s plus 1 plus b times s minus 2 equals s minus 1. So a plus b equals 1. That's just the s terms. And then a minus 2b equals minus 1. I'm just equating all of the non-s terms. Okay, so I'm going to subtract the bottom from the top, and I'm going to get 3b equals 2, which means b equals 2/3 and a equals 1/3. Okay, so my solution x bar of s is equal to 1 over 3 times 1 minus 1 over s minus 2 plus 2 over 3 times 1 over s plus 1. And now finally I'm going to inverse Laplace transform this whole thing, and I get x of t equals 1/3 times the inverse Laplace transform of this plus 2/3 times the inverse Laplace transform of this. Numbers just pop out. So this is 1/3 e to the 2t plus 2/3 e to the minus t. So it's actually not that complicated. It's pretty straightforward. If you were going to solve this using the traditional methods, it might be a little easier just to plug in e to the lambda t and solve the characteristic equation. But then at some point, you're still going to have to solve for the initial conditions for the coefficients. And it all ends up being about a wash. Okay, any more questions about how to solve this? Okay, let's do the general case. So this is kind of remarkable. Even though the actual by hand steps might be a little more complicated, what's remarkable is that I took my differential equation, and when I Laplace transform it, I turn all of the differential equations and rates of change in calculus into essentially an algebraic equation. My solution is just a polynomial divided by another polynomial. This is algebra. So we've taken calculus and turned it into algebra by doing the Laplace transform. This is a huge simplification. Even just conceptually, it's a good simplification. And this is going to make it so that we can actually solve PDEs that we couldn't solve by hand before. Okay, so the last thing I'm going to do is show you the general case. All right, so let's say that I have a really high order differential equation like x nth derivative plus some coefficient times the n minus 1th derivative plus dot 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 plus a2 x double dot a1 x dot plus a0 equals 0. Okay, what information do I need to make this a well-posed ordinary differential equation with a solution? Initial conditions. So what initial conditions do I need? I need all of the n minus 1 to 0 derivatives of x. Technically, I could have any linear equation in those being satisfied. I could have a whole equation like x dot of 0 plus x0 equals 2, and it could be really nasty, but I'm not going to do that. So let's say that my initial conditions look like this. Okay. So this is a well-posed ordinary differential equation with a solution. Okay, we can solve this using normal methods.
X to the a naught.
Yeah, thank you. No derivative, but there is an x. Good, thank you. Okay, so the first step is that we have an ordinary differential equation. The second step is that we're going to Laplace transform everything. So I'm just recapping what we've done for the simple case, but for the more general case. Okay, so we take the Laplace transform of both sides, and we get something like s to the n x bar minus dot 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 minus b n minus 1. plus a n minus 1 times s to the n minus 1 x bar minus dot 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 minus b n minus 2 plus dot 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 plus a1 s x bar minus b0 plus a naught x bar equals 0. All I'm doing here is I'm just taking the Laplace transform of each of these x derivatives, and I'm plugging them in where those terms go. And I'm writing a lot of dot, dot, dots because I don't want to think about what's between them. Okay? So this is, Laplace of the nth derivative of x. This is Laplace of the n minus 1th derivative all the way down to Laplace transform of x dot and x. Okay, good. So what's the next step? What's step 3? Combine all of the S bar terms and put all of the initial condition terms on the right-hand side. Okay, so I have step 3 is essentially combine all of the x bars and then put all of the initial condition terms on the right-hand side. So we're going to have something like, now how do I know how all of the x bar terms are going to combine? How do I do this really, really easily? What's the characteristic polynomial? So it's just s to the n plus a n minus 1 s to the n minus 1 plus dot 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 plus a 2s squared plus a 1s plus a naught. X bar of s equals, okay, this is just collecting all of the x bar terms. It's going to give me the characteristic polynomial in s times all of the x bar terms. And then this equals everything else. And I'm going to say that it's a polynomial in s. So it's a poly in S with coefficients given by the A's and the B's. And really, this codes up all of the initial conditions. Okay, so all of the dynamics of my differential equations, forget about the initial conditions. For any initial condition, my differential equation has some dynamics, e to the lambda t's. That's all on the left-hand side. And all of the information about the initial conditions is on the right-hand side. In fact, every term on the right-hand side, its coefficients are directly in terms of my initial conditions, b's. And so I'm just going to call this some poly of S, and it's parameterized by a's and b's. This is just shorthand notation I've introduced because I don't want to keep writing down this polynomial because I don't know what it looks like. It's a nasty polynomial. I might ask you to write this down on a homework. That would be a reasonable thing to do. Because it actually turns out that the form of this polynomial in initial conditions is quite interesting and comes up a lot in mathematics. It's a very useful matrix. It's called, oh, it's got a name. Okay. All right, so what's the fourth step? Okay, so why am I dividing? Let's be more clear. Why am I dividing by the characteristic polynomial? I'm isolating my solution. Okay, so I want x bar of s equals this polynomial, p of s parameterized by a and b, parameterized by my initial conditions, divided by my characteristic polynomial, s to the n plus a n minus 1 s to the n minus 1 plus dot 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 plus a 1 s plus a naught, my characteristic polynomial in the denominator. Okay, we're getting super duper close. Only 2 more steps. Okay, what would you do at this point? Before I do partial fractions, what do I do?
Rewrite the denominator.
Okay, so you're both right. In my notes, I've essentially skipped steps and then tried to re-justify them. So what we do now is we break this up into a partial fraction of factors of the denominator. So we factor the denominator into all of our eigenvalues, all of our lambda 1, lambda 2, lambda 3s, all of the roots of this. There are n roots. Each of those is a lambda. And I'm going to write this as some coefficient 1 divided by s plus lambda 1 plus some coefficient 2 divided by s plus lambda 2 plus dot 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 plus cn divided by s plus lambda n. And the missing step here is that essentially I factor the characteristic polynomial into s plus lambda 1 times s plus lambda 2 times dot 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 times s plus lambda n. So I break it up into n monomials. These are given by the n roots of this characteristic polynomial. Things go really badly and get really weird when I have the same root multiple times, and it gets a little complicated, but let's not think about that for now. It's not terrible, it's just a little more complicated. It's actually easier in Laplace transform than in the time domain because we can solve this with the Laplace transform. Okay, and so the last step is step 6. So I don't just want to factor into the polynomial, I also want to solve for C1, C2, dot, 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 Cn, and this is the method of partial fractions. Okay, so what's the last step? Now that I have x bar in this wonderful, simple form of a sum of monomial fractions, what do I do? Inverse Laplace. And this is actually easy to inverse Laplace because I know what all of these terms are. So x of t equals c1 e to the minus lambda 1t plus c2 e to the minus lambda 2t plus dot 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 plus cn e to the minus lambda n t. And that's my solution. Okay, so the general form, you can do this for any ordinary differential equation that's linear. It becomes super simple. If you do this for a nonlinear ODE, where do you think you'll get stuck? Let's say I Laplace transform some really nasty, horrendous ODE like x dot x double dot plus x squared equals cos of x. So I can certainly Laplace transform every term in here. Maybe forget the cos of x. Let's just make this a 0, make it easier. Yeah, so essentially everything goes bad starting at step 3. And that gets really bad in the partial fraction step. So I could take and write s x bar minus x naught times s squared x bar minus x minus s, is it x dot? X naught minus x dot naught plus x bar squared equals 0. But now I can't just solve for all of the x bars on the left-hand side. I don't just get some polynomial in s times x bar. I have x bar squareds and another x bar squareds, and everything is super complicated. Okay? Not to say it's impossible to solve. I could solve for x bar equals some square root of some polynomial in s. But how do I inverse Laplace transform this? I can't write this as a nice sum of easy fractions, right? So it gets more complicated, but it is possible, in principle, to do some of these things. So I don't want you to think that Laplace transforms are limited to just linear or ordinary differential equations. They're not. Okay, questions about the general form before I go on a little bit farther?
Yeah.
For the nonlinear system, would you then, to simplify it, would you linearize it about in some neighborhood and then transform it into the Laplace?
So it's interesting. Before computers, people still wanted to solve these problems. And so they wrote gigantic books on how to solve the inverse Laplace transforms of these nasty functions for common differential equations like this that are popular, that pop up all over the place for beams and for elastics and drum membranes and optics and all kinds of common nonlinear differential equations. There are entire books of how to solve these Bromwich integrals to inverse Laplace transform, and they're all coded up in Mathematica. And so it turns out there's actually an amazing wealth of techniques to solve these things. What you can often do is you can often write this as a product of simple things you can inverse Laplace transform. And then the inverse Laplace transform will be the convolution of all of those terms. What we'll find on Friday is that even for really nasty, hairy problems, we can still do inverse Laplace transforms numerically sometimes. So even if I don't know how to inverse Laplace transform something, I can still do it numerically a lot of the time. Okay. Other questions? Okay, I have just a couple more minutes, so I'll tell you a few more things. So the next thing I'm going to tell you kind of motivates what we're going to do on Friday, which has already been alluded to, which is the nice thing. One of the nice things about the Laplace transform solution to ODEs is that it's very easy to add an external forcing term without really messing up anything. So it keeps it very clear what's happening. In the notes for 564, I did write down the solution for external forcing one time, and it was a little complicated in terms of a convolution integral. And we'll see that it basically is much easier in the frequency domain. So if instead of my ordinary differential equation equaling 0, let's say I have it equal u of t, some external forcing. This is the basis for all of control theory, to have this external forcing u of t here where I can actually force my system and make it do something I want. Now I still need initial conditions. And I still go through the exact same steps. I Laplace transform. And I get the same thing, s squared plus 5s plus 4 times x bar of s. And it equals all of the terms in terms of my initial conditions, which I think was 2s plus 5. But now I also have the Laplace transform of my forcing term, plus u bar of s. Okay, so these are all of my initial conditions. And this is my forcing. And so now I can say that my function x of s, x bar, is equal to my original part, my homogeneous solution with my initial conditions, 2s plus 5 divided by my characteristic polynomial. But now I have an additional particular solution given by u bar of s divided by s squared plus 5s plus 4. The great thing about Laplace transform solutions is that if I inverse Laplace transform this, I still get the homogeneous solution to my initial conditions. And I also get this additive term due to forcing. And we're going to see that this is the convolution of my forcing with something interesting, which is the inverse Laplace transform of the characteristic polynomial. Okay? So this is just kind of leading up to the lecture on Friday. We're going to start right here, and we're going to start seeing what this term does to the differential equation in terms of this very special 1 divided by the characteristic polynomial. So we'll even give it a name. We'll say g of s equals 1 divided by the characteristic poly is my transfer function. Okay, and we're going to start looking at the properties of this transfer function, why it's useful, why it's much easier to write my differential equation this way with forcing. And we'll be able to do cool things like design this u function to make this system look more like what we want. So we can design a control strategy u that stabilizes an unstable system, like a pendulum, or does all kinds of other cool things. Okay, that's it for today. Friday we'll talk about this system with forcing.